Okay, so good morning again, and welcome back to the last day of the EasyBuild user meeting. So I'm happy to talk today about Sarus, that is a highly scalable Docker container runtime on HPC systems. So this presentation has been contributed by a colleague of mine, Alberto Madonna, who works at CSCS in the operations unit. So his group has developed the tool. I'm again Luca Marsella from the Scientific Computing Support, of my experience with Sarus from the user point of view, in the sense building a Docker container, running that on the system, especially with two applications. My experience is with Quantum Espresso and CP2K. So if you have questions that are specific for developers, unfortunately I might not help very much, but I can forward the questions later. So with this disclaimer, let's begin. I'll begin with an introduction on the containers on Linux ecosystem, and in particular the timeline of containers at CSCS. And then we will go through the Sarus development and Sarus features with OCI hooks, and then a use case with an Intel NKL and MPI Vidia container. And finally, I will show some performance tests that we have done with Sarus on the main system at CSCS. So containers, you probably already know, they are isolated environments to run applications and services, and the container image contains everything you need, so software and dependencies. The advantage is that they are portable, they should be easy to build, and reasonably quick to deploy. And the picture just shows you the difference between a virtual machine and the container. Now, in the Linux ecosystem, there are some of the tools that were already available in the market when the Sarus project started at CSCS. And, well, the most famous is Docker, which is not really meant for HPC, and HPC-focused solutions are highlighted in the cloud on the right side. So at CSCS, we had some experience with Shifter. We also have the possibility to use Singularity on our system, and we have this timeline just to show you how the development of the Sarus idea has begun. So back in 2015, there was an early Docker evaluation for accessing GPUs, and in 2016, the Shifter container runtime was started to be adopted at CSCS, before on the test system, and then in production in 2017. There was some kind of update on Shifter, so the name was changed to Shifter NG in 2018 to include some more features, in particular the command line interface, more Docker-like, and the image manager. So finally, after the more or less end of life of Shifter, due to the difficulty of developing further the features needed at CSCS, a project started in 2018 to develop Sarus. And finally, it was eventually in production last year in November on Pitstein. So let's see then what were the requirements for the new container runtime and the features that have been put in place. So the requirements, well, first, the runtime container needed to be suitable for HPC. In particular, most important things, we have diskless compute nodes. It must be compatible with the low workload managers, and it must acknowledge the parallel file system. Then the developers wanted to have it pluggable with vendor support, in the sense of importing, having the possibility to include hooks, which are OCI compliant. In particular, the NVIDIA Runtime Toolkit for containers, the MPI hook, and also RDMA access, so the GPU direct access. One more important requirement was the user experience, in terms of having a Docker-like command line interface and Docker Hub integration, so the possibility to pull images from Docker immediately. Also, to have a writable container file system, which is useful because you want to mount runtime on the container your local folders if you have to run some benchmarks, importing input files, these kind of things. And last but not least, the admin side. So from the admin point of view, they wanted to have some tool that could be easily installed and easily customized with OCI hooks. And also to have a, let's say, not a big burden for maintenance. Now, in the end, the Sarus features, Sarus as it is in production now, are as follows. So as I mentioned, suitable for HPC means that they managed to have a single squash file system image that is parallel file system friendly, and then the RAM file system for fast image access. It is compatible with the workload manager. We have Slurm at CSCS, and it features native GPU and MPI support. They plugged also vendor OCI hooks in the tool, so the NVIDIA Container Toolkit and other OCI hooks that were adapted at CSCS, in particular the MPI hook. And then it has a Docker command line interface. It has overlay FS to write on the container file system at runtime, and it keeps also identity and file permissions for the user files. And from the admin side, it is a single executable binary that is easily deployable, and you can customize easily that with OCI hooks. You'll see that in a while. And it's mainly based on Run C, so it has many features that are already you can see in Run C. And from the maintenance point of view, it is tested with unit test coverage that is around 84% of the features. Now, just to give you an idea of the most important things from my point of view in terms of the user experience. So if you use Sarus on Pitstein, you just load a module called Sarus, and then you have a command line interface that is exactly like Docker. So you can do Sarus pull to pull the Docker images that you want to use from Docker Hub. Sarus load if you have a local archive that you have somehow prepared with your container tool and you copy to the system and you want to load it on the runtime container. Sarus images to check the images that you have already loaded. And then the other commands like RMI to remove the images and Sarus run to run your container. So that's exactly a copy of what you can see with Docker if you have experience with Docker already. Now, the architecture overview of Sarus is as follows. You have, let's say, Sarus, which is aware of the parallel file system below that. It takes either the containers from the Docker Hub, so the Docker image repository, or from an archive file that you can have locally. There is a set of JSON files for the configuration of the tool with some restrictions of the permissions and capabilities of what the user can do. And then it communicates runtime with the OCI hooks in order to get, let's say, the host libraries, or the runtime NVIDIA CUDA driver, the MPI library of the host, and all these hooks will be shown in a bit more detail in a while. So OCI hooks. So OCI stands for the Open Container Initiative, an open governance structure to create open industry standards. And the specification defines what the interface for the plugins that you want in your runtime container must have. So in this case, these are external programs that will use this. External programs will use this interface in order to customize your container at runtime. In particular, in our case, as I mentioned already, especially with a focus on the NVIDIA driver, NVIDIA libraries, and the MPI libraries. Now, at CSCS, the OCI hooks, but can you still hear me? Okay. At CSCS, the OCI hooks that we use were the NVIDIA Container Toolkit that is already deployed by NVIDIA, and then a set of hooks that were developed at CSCS and are bundled together with Sarus. The most important ones are the MPI hook, which is based on the MPitch library. So it ensures a native performance of your container application in the host MPIC based environment. So in particular on our system we have Cray MPIC, and which is compatible with ABI compatible with the MPIC 3.1.4. Then there is the glibc hook, which replaces the container glibc if it is older with respect to the host glibc to ensure compatibility. Otherwise, the MPI would not work inside the container at runtime. Then there are other hooks that have been developed like for, well, developing still for developers' needs and also admin purposes, like the timestamp hook, for instance. The slurm sync hook also kind of synchronize the activity of the workload manager with the internal container applications. So the NVIDIA Container Toolkit, as I already mentioned, is part of the NVIDIA Container Runtime that you can find on GitHub. It imports the NVIDIA driver and the GPU device files into the container. So when you build a container, of course, you have just other files and library files, and then you need a runtime container, the runtime NVIDIA files for the container customization. In general, it provides native performance without any input from the user, so it's completely transparent, the use of this, or the hook from the point of view of the user. And as an example, there is here a small test of the SDK and body sample of NVIDIA for the native versus container runtime, which is compatible within the standard deviation. The MPI hook replaces the container MPI library with a host library that you find on the host system at runtime in order to achieve the native performance. So the basis for using the host MPI library is that the MPI library that you have used inside when you built the container must be ABI compatible with the one available on the host system. So on the website mpich.org/ABI, you find a list of ABI compatible MPI libraries. In particular, when we build a container with the GNU, we always use MPich 3.1.4. I had some example, which I showed later with the Intel MPI library, which is also ABI compatible. On the page is mentioned only in Intel 2014, but I use Intel 2019 without any issues. And then you can find other libraries there. Now, also the MPI hook, as the NVIDIA Runtime Toolkit, is completely transparent to the user. The user just needs the command line interface of Sarus to use the flag --MPI to activate the MPI hook that will replace the container MPI library with the host one. Here there's an example of what you can get as a comparison for the OZU benchmark, the all-to-all latency benchmark of the Ohio State University for MPI library on the native system and using the container MPich. And as you can see, they are practically overlapping. Now, the part that it's quite interesting, I think, from the user point of view is to have a practical use case in which you can easily build a container that you can run then on the HPC system. You probably have experience in building containers for other applications, but then running on an HPC system at scale might be a bit tricky. So let's see. The typical user workflow would be, well, the usual stuff that you have done probably already with Docker for other applications, just that you create your Docker image, then you push it to Docker Hub if you have the right to do so, because, for instance, there might be licensing issues, so you might not publish all the images that you can produce with licensed software that you have on your local machine. If you can't do that, you just have to save your image as an archive and you copy that to the HPC system. And then once you get on the HPC system, then you pull your image either from Docker Hub or you copy the local archive to the local storage and you run at scale. Now, in my case, I wanted to give you an example of what I've done with a container based on an NVIDIA image that featured the CUDA Toolkit 10.1 based on Ubuntu 18.04 that you can find on Docker Hub under the link that I paste in the slide, and building on top of the NVIDIA basic image, the Intel compiler with Intel NKL and Intel MPI, in order to use this image as a basis for building applications with Intel compiler and running then on the production system, the production HPC system at scale. So as you see here in the shell-like screenshot, in order to build the Intel compiler, you just follow the same steps that you would do on a laptop. It's just that you are doing that inside a Docker file that will be then run by Docker on your platform where you have Docker installed in order to build a container. Everything here is pretty straightforward, except that you need to have a license for the Intel compiler, so that's probably the trickiest part, and that's why you cannot then distribute the image that you have built for licensing issues. So I couldn't push this image on Docker Hub, and then I will save it later to a tar file. Now, the tricky part here is about the runtime Intel variables and the library path. So after you build the Intel compiler, in order to use correctly at a later stage the compiler and all the libraries that come with the compiler, you need to tell you need to write down some profile files. Let's say I had decided here to write a file that I called intel.sh under the profile.d folder that I will source as runtime. If you use a login shell in general, it is already sourced when you open the container next time. Then that's one thing. A second and most important thing is to let LD aware of the library path if the library path is not standard. So in particular, Intel MPI libraries are installed in non-standard locations in terms of the Linux experience. So what I did is just creating a specific intel.conf file under the ld.so.conf folder and run ldconfig afterwards in order to make the libraries available to the linker at the linking stage. So all this is useful when then I want to build an application. So suppose that now I have my Intel image based on NVIDIA CUDA, and I want to build, in this case, Quantum Espresso, which is a scientific application used in material science simulations. So as I said, since I prepared my Intel container with some specific profile files to source Intel variables, I will start here from my Intel image using a login shell. So the shell with -- login as an option. Then I run ldconfig because I already prepared in my container the Intel configuration file under the ldconfig folder so that all the libraries will be found runtime by the linker. And then once I do these steps, I can start building my application in the usual way. Here, I just download the tar package, unpack, and so on and so forth. You can always build that with EasyBuild or your favorite builder, also inside the container. So that's entirely up to you. It's a standard Linux environment. Once you build your container, as I said, I cannot publish this container on Docker Hub because it features the Intel compiler, which has a restricted license. So I did a Docker save to save an archive, copy the archive on the local storage of the HPC system, and then once I load on the HPC system, I just do module load Sarus, and then Sarus load my tar file. Then I choose a tag name for this particular image, which I call QE65A1. That's the versioning name of the Quantum Espresso 6.5 release with GPU. Once you load it, it takes some time. You can run it on the compute nodes. And to run it, you just use in Slurm the srun command. So you choose the number of nodes, number of tasks as usual. And then there is the Sarus command invocation with the flags like Sarus run, --MPI activates the MPI hook, which will use the local MPI library on the HPC system. Then, as you see, I use also --mount. Since the container file system is writable, I can mount on the container file system all my input folder with the input files that I need for running my application. In particular, in this case, I mount it on a folder. So the local Scratch file system with my benchmarks folder is mounted in the destination that is called USR local benchmarks on the container. So when I then load my image, load library QE65A1, I then run the command in the container bash-c. I cd to the benchmarks folder that I mounted with my input files, and I run the executable, which is called, in the case of Quantum Espresso, pw.x, and I pass the input files as I have named them in my benchmarks folder. So this is quite easy. The tricky part is just activate the MPI hook with --MPI and mount the input folder where you have all your files. Other than that, the procedure is the same as you would do that in a normal workload manager batch script in order to run the application. So there's not much difference. And to let you then have an idea of what kind of performance you can get with respect to the native run of the application, I'll show you some performance tests. I'll begin with some tests that have been done by my colleagues, and then I will end up with the Quantum Espresso application that I mentioned already in the previous steps. So we start with Romics, which is a classical molecular dynamics simulation package, which is probably already known to you. This is Gromax 2018.3, and you can see on the left side the performance in terms of nanoseconds per day produced by the simulation engine, and on the right side it's speed up with respect to ideal. So due to some statistics here, because the run was conducted several times, there might be little fluctuations between the native and the container outcome, but in general it is statistically compatible. As you see, that the error bars are more or less covering the possible difference that you have in the performance of the tool. So here we reach 256 nodes, so each node of the system has, as you probably have heard in my talk yesterday, it has one Haswell processor and one Pascal GPU. So this is quite, let's say, I would say, not the largest simulation that you can have, but a quite large simulation. So the fact that Sarus can cope with this range of nodes it's remarkable. Then we have a test with TensorFlow and Horovod. So this is in the field of deep learning, data science simulations. And also here, we reached an even larger number of nodes, like 1024. And the behavior of the application in the container run with Sarus is compatible with the performance that you get with a native one. Same for Cosmo, which is a code used for numerical weather forecast simulations, and it's used by the Meteo Suisse institution in Switzerland, for instance. In this case, you see the weak scaling curve of two different simulations with two different resolutions and grid sizes. Now, then I wanted to show you the simulations that I've done with Quantum Espresso. So they're probably not as beautiful as the ones that you see now with Romics, TensorFlow, and Cosmo. But I wanted also to give you an idea of what you can get in terms of memory consumption in case you have an application like Quantum Espresso that has sometimes some, let's say, some drawbacks in terms of memory usage and parallel file system usage. In particular, Quantum Espresso is normally a high demand of memory runtime, especially if you run on not so many nodes, and it writes down an output file for each MPI task you use. So it could be a bit, let's say, demanding in terms of parallel output. Now, I used, in order to show you the performance of Quantum Espresso, 4 benchmarks that are used by the developers of Quantum Espresso. You can find on the GitHub page of the application. They are called AU Surf 112, so the surface of gold, 112 is the direction. In the case space, psi watt, GRIR, and then the number of atoms, 443 or 686. So the simulations here, the benchmark goes from the smaller ones in terms of number of atoms to the biggest one. And you can spot, let's say, the difference in terms of the performance between the native application, which is in blue, and the Sarus in the container, Sarus runtime in the container, which is red. So at the lower node counts, I start here from one node on the left side with the smallest benchmark. The difference is quite remarkable. And after the experience with Sarus, we realized that it's due to memory, in the sense of memory requirements. For some reason, Sarus requires some memory overhead, especially we noticed that with Quantum Espresso, which is already memory intense. And when you distribute the simulation over a large number of nodes, this effect disappears. But you notice that at lower node counts. While when you go to higher node counts, the behavior is more or less overlapping within the statistical error. So that's the same behavior that you see on the right side for a slightly larger sample. And here again, you see on the left side an even larger one with 443 atoms, where the two native and container application behave in the same way. And on the right side, you have the largest benchmarks that I could run with Quantum Espresso and Sarus. And here you see there are two missing dots, two missing points for the Sarus that are the lowest node counts, 8 and 16 nodes, where actually the memory requirements of Sarus were causing the simulation to go out of memory on the nodes. And that was just by, let's say, not so much respect to the total memory available on the nodes, but unfortunately, that was causing the simulation to stop. So this is the only real drawback that we have found until now. This was done in last summer, so before the production version that was deployed on the system in November. But apart from that, the behavior of the container application was almost overlapping with the native one, with no major performance drawbacks. Also, it has to be said that in this case, with such a large sample, like the one shown here on the right, you wouldn't run, of course, on 8 or 16 nodes. So the interesting behavior here is the one at the large node counts, which is still within the statistical error. Now, in conclusion, so Sarus is a container engine for HPC system, which is compliant with the OCI standard. It provides all native performance, close to native, through the hooks that are implemented, that are bundled in the runtime container. It provides a consistent user experience with Docker, so the learning curve is really minimal if you are already used to Docker. And then from the admin point of view, because you might want to try that also as an admin, it enables to use standard, the open components on any HPC system. And there's an extensible architecture because you can plug in vendor hooks that improves also maintainability. Some useful links. So Sarus is open source. You can find that on GitHub. You can have also the user documentation on the user portal CSCS. And on the read the docs of Sarus, there is a quick start guide for installing Sarus on your HPC system and running that. The official the official guide, the longer one, is also available on read the docs. And then I enclose also a link with best practices to write your Docker files. So last but not least, so what is a Sarus and why the name? So apparently Sarus is a crane, so this is from Wikipedia. And just a note, just to avoid any confusion, not to be confused with this, which is a Soros. So thank you for your kind attention.
Any questions from the floor?
Or in the chat.
Well, it sounds pretty much similar to Singularity.
Yes.
So why another?
Yeah, okay, so I was not involved in the development, and the development started in 2018. At that time, my colleagues, let's say a small team of people, evaluated the tools on the market. among them Singularity. There was also Shifter, which was already in use at CSCS, and a few other ones. Also the Run C, which is the basic one provided also by Docker. They tried to, let's say, match all the features that they wanted, and sometimes there is also the part of, let's say, user experience that is also personal, in the sense personal feeling. Sometimes people tend to, let's say, they want to customize things in a different way. So that's why they probably decided to try for something new rather than adopting Singularity as it was at the time. I'm not sure about now because, of course, the tool evolved also in the time. So, yeah, it's also possible to use Singularity, but we have it, we provide it on the system. So, let's say each user could also try both and evaluate what's the best for them, also in terms of usage.
Okay, and related to that, am I right that the Sarus consumes normal Docker files, or is this some special format?
No, it uses just the standard Docker file that you can have. So not the Docker file, but the Docker image, let's say. So you can pull it directly from the Docker Hub, or you can save it as an archive with a Docker command, Docker save, and it uses exactly the same format. So there's no intermediate conversion needed.
So what does OCI compliance mean then? Does that mean that if I make an image in Singularity, I can run it in Sarus, or is that not compatible? Or the other way around?
OCI compliance is for the hooks, so the plugins, let's say, that you want to put in your, that you want to use to customize your image runtime. So there is a standard for that, and that's more for the admin side. So it's quite transparent for the user in the sense the user doesn't need to know anything about that.
But you can consume Docker images. Could you consume Singularity images, or is there a reason you couldn't do that?
Well, I think Singularity uses a different file format with respect to Docker. So no, you can't use it immediately. So you need standard Docker images.
And can it create Docker image from this Docker definition files?
So creating Docker images is demanded to the user. In a sense, Sarus is a runtime container. So you need to have a container image. In order to build it, we are evaluating a solution which is not Sarus anyway. So it's something else to build on the system. Typically, you build on your laptop or on a virtual machine somewhere. So a simple, maybe Linux system where you have installed yourself Docker with root privileges or anything related to that.
Okay, so the workflow would be that the user creates the Docker image from a definition file with Docker on his local machine and then moves it there?
Yes.
Okay.
Yeah, that's the idea. We are already evaluating a solution to let users build their images on our system, but it's still, it's not yet in place.
So on the admin side, could I just try out Sarus today without root privileges?
Yeah, you can download it from the quick start link that I provided before, so it's here. So the third link here, there is a quick start guide. It should be pretty straightforward. What's
the requirement as regards the OCI hooks then? So say like we have a custom MPI implementation, which is MPIC based in Uli. There's a requirement from their side to support the hook. Is that right? Do I understand that correctly?
Well, so from the MPI point of view, if it is ABI compatible with the list provided on the MPIC website, there shouldn't be any issue.
Okay.
Yeah, so ABI compatibility is important for the user that builds the container because they need to build with an MPI library that actually is compatible. Otherwise, there's no way. It's compatible with the one that is present on the host system.
But you query the MPI somehow to know where the libraries are, right, or something, or like I don't know.
If you, from the user point of view, if you install the MPI library in a standard location, you don't have to do anything apart from running your ldconfig file, ldconfig for the link of your application. What I've shown in my example was in the case you install the MPI library in non-standard locations. It's a bit more tricky. But
how concerned is CSCS that when people start building container images wherever, whether it's on their laptop or somewhere else, that it's not optimized for the architecture where the container will be running, right? They may have a Haswell laptop and you're running on a Skylake, so you're going to lose a lot of performance just by not properly cross-compiling or...
Well, so in this case, for instance, of Quantum Espresso, I built that on a virtual machine and I think the processor was some old Sandy Bridge maybe. So the important thing, I used MKL libraries and I linked dynamically the libraries. If you link the libraries dynamically, why I've shown an Intel example? Because on the host system, that is our HPC system, we have the Intel compiler with the MKL libraries. The good thing about MKL, it has the same name scheme. You use the MKL root environment variable, you find the path to the libraries. So your executable will look for the host libraries and not for the libraries that you have used when you built it. I had already some example that I did with a GNU compiler, building something using my own built, let's say, linear algebra libraries like Scalapack on the host system, and it was a disaster because it used sorry, not on the host system, on the container, it used the container libraries that I used when I built it. So running runtime on the HPC system, it didn't find the same name, because unfortunately on the Cray system, if you use the GNU compiler, you have the scientific libraries in a package, in a module called Cray libsci, so scientific libraries. It has a completely different library name scheme with respect to what you build with Scalapack, OpenBlast, whatever. So it cannot find immediately that libraries. It uses the libraries that you have built inside your container. The performance is horrible. Then it depends on the user to, actually that's also a trick here, to use dynamic linking with libraries that can be found on the whole system. Otherwise, the performance cannot be matched. So I suggest to use the Intel compiler if you have one, because it can be used on any HPC system with Intel compiler that features also MKL libraries.
But so the expectation is that the users that use CSCS and this runtime, that they get that part right to get good performance.
Yeah, it might be a bit, let's say, not so straightforward. Yes.
Yeah. Okay.
Yeah.
Any other questions for Luca? Okay, let's wrap up here, and then we have two more side presentations by Lynn from University of Melbourne and Alexander.